friends, welcome back. Now let's begin our journey into synchronization among the processes. So let's start how software can help us in synchronizing the processes. In this regard, let's begin our journey with an algorithm called the Peterson's solution to the synchronization problem. So how to handle a critical section? That's what the solution is under the Peterson's solution. So it's a classic software based solution for achieving mutual exclusion among the processes. Here no hardware instructions are used, it's purely done on the software. And this Peterson solution is restricted only to two processes. So either process I or process J, only two processes are active any given time, then Peterson's solution comes to our aid. Here we try to alternately make sure that the two processes are in the critical section in an alternative basis if both want, but if only one of them wants to enter critical section, we don't have any issue of synchronization. So only the issue comes when both of them want to enter critical section, then we make sure that they enter into critical section on alternative basis. And this Peterson solution believes in the cooperation. That means if one process wants to enter into critical section, it first tries to allow the other one. If other one also willing to enter, then the process I first like to say it is let J completes its critical section part, then let me use it. On the same way, if it is process J wants to enter, then it says I want to enter the critical section, but anyway if I is already waiting, then let I complete the job, then J let me continue. So it is cooperatively done. And here we have two shared variables, one is a flag and other is turn. Flag, we have two flags, one for each process, one flag I and one flag J, whereas turn is only one variable, and this can be either I or can be either J. So if it is I, then I can continue, and if it is J, then J can continue if they want to. So that is the meaning of the turn. So whenever a process wants to enter critical section, it first raises the flag, says that I want to enter, and then cooperatively says let other continue to enter, I will wait. So it makes turn equal to the other, and if other is already waiting for that, then it will get a chance to get into critical section. So here cooperatively they try to work and make sure that each one gets chance, and alternatively they will be getting chances. So we have two flags, the one for each process, and says this flag is used to announce that any process wants to enter critical section, will raise a flag and say yes, I want to go into critical section, and then the turn tells who can get into. And that's a code which we use for ensuring the critical section problem is solved through this. So here this is for the process I, and whenever process I wants to get into the critical section, it will say yes, I want to get into critical section, so raises the flag. So process I raises flag says I want to enter critical section, but also says that let J comes first. If J is waiting, then let J come first. So let J get into critical section. So that means if J has already raised his flag, so flag J is true, then now we have just made turn equal to J, so turn is J, this is also true. And if flag of J is already raised, then both of them are true, and these two are operated by an AND operation. That means when both are true, then this whole thing is true, and we can see that this while doesn't have any instructions to execute, but it is just one single thing. So what is it trying to say? End of the instruction, end of the line, we have a semicolon. It says that as long as this is true, keep running this. So while true, yes it is true, then again while true, yes true, again. So as long as flag J is high and the turn is J, it will remain in this line, keep executing this line again and again and again, which means that process I has nothing to do except waiting. It cannot enter into the next line, which is critical section. So that is what it is trying to say. Flag J is high means J wanted to enter into critical section, and here our process I wanted to enter critical section, therefore it raised its flag. Flag I is true, but it said turn equal to J, therefore now the value of the turn is J. So flag J, if the other side, the process J also has raised flag, then the flag J will be true, and turn equal to J, if this line is just executed, then this is also true, and hence this condition is true, and this keeps waiting and waiting and waiting. Therefore process I keeps waiting. On the other side, the same thing is written on the other side, but only thing is flag J equal to true. Now it says turn equal to I, but what happens is who executes this turn equal to the sequence of executions turn equal to. If process I is executing, then it says turn equal to J, and if process J is executing, it says turn equal to I. Then who executes these lines first? We'll write it there in the position turn, and who executes next will overwrite it. That means at the end, who has written last, that value will remain in the location turn. So if I has written last, then you will find J there. If J has written last, we find I there, because cooperatively they are saying process I says J should do first, and process J on the same way saying that I should do first, and who said it last matters. Who said first doesn't matter, because we are overwriting on the variable turn, and who has written last, that value remains there on the location. So depending on who said it last, that one will matter. So if I has said it last, then turn value will be J, then this remains true, so I waits. If J had written last, then J had written turn equal to I. Therefore in this case what happens is flag J, yes it is true, but turn is I, therefore this is not true. This is for process I, this is not true, therefore process I will enter into the critical section. And once process I entered into critical section, we should confirm that at end of the critical section we should take out our flag and say that we are no more in the critical section, so anyone else can get into critical section. So flag I is made false, and then it continues in the remainder section. And if you can see that this whole thing is put under another while loop, and it's an indefinite while loop, and these two parts are repeated alternately, once in the critical section, then the non-critical section, then critical section, non-critical section. That means whichever part of the code of process I needs to use the shared resources, that becomes critical section, rest all will be non-critical section. So some part critical, then next part will be non-critical, then somewhere else critical, then non-critical, then critical, non-critical, critical, and that way it continues. So it's a indefinite do loop or while loop, and so we have an alternate critical and non-critical sections running. But what is important here is, before entering critical section, we ensure that we are free to enter into the critical section. So we ensure that, and that we make sure that it is our turn to enter, and once we are sure that it is our turn to enter, then we enter into critical section, and finally say that we no more want to enter critical section, we are out of it, and then continue with that. Next time when we want to enter critical section again, then this whole circus is repeated. So what's thing, how the Peterson solution is working? So the three conditions, if you remember, that are to be satisfied for a critical section. Number one, mutual exclusion. Yes, because of this, either I will be in the critical section or process J will be in the critical section, cannot be both together, and therefore, because turn can be either I or can be either J, it cannot be both. Yeah, flag I can be true, flag J can be true together, but turn value is either I or J, not both. Therefore, either process I's while loop will be in the indefinite while loop, or process J's will be in indefinite. That means only one will be allowed. So mutual exclusion is preserved. Then process requirement is satisfied, because here other processes are not participating in deciding who should go into the critical section next. It is the processes who are interested in entering into critical section only are voting for it. There are two processes waiting for entering into critical section. Then I says let J go, J says let I go. So cooperatively they are doing. Therefore there is definitely progress. And bounded waiting. Yeah, because the critical section sometime has to enter, sometime has to end. The moment that critical section ends, the flag goes false, and if that flag goes false, then the other side, the while statement, goes false, and hence it gets into critical section. So therefore it cannot be unbounded waiting, it has to be a bounded waiting. So let's take up what happens step by step. Let's assume that only Pi wants to enter critical section. Pj is currently not interested in any shared resources to be used. So let only Pi wants to use shared resources, so it should enter critical section before using them. So assume only Pi wants to enter the critical section. In that case, this is the code for the Pi. So first instant flag I becomes true, then turn becomes J, then while flag J and turn equal to J. So we have said that only process I wants to enter into the critical section. Therefore the flag of J is not raised, so it is false. If it is false, then though turn is equal to J, the second part is true, but the first part is false. Therefore this AND operation says it is false. Therefore this while loop breaks, and therefore the Pi enters the critical section. Once the critical section part of the Pi is done, then it finally says flag I is false and says that my critical section part is over, so anybody else can get into critical section, I don't care. So it makes flag I equal to false and then continues. Now imagine both want to enter the critical section. Pi also wants to enter, Pj also too wants to enter. So let's look the what it can happen. So let's assume that these codes are executed, maybe interleaved. So some part of Pi is executed, then some part of Pj is executed, one after other, interleaved way. Because there is only one processor, so either Pi's line will be executed or Pj's line will be executed at any given time. So let's assume that they are running in an interleaved manner. So to begin, let's assume that the flags for Pi, Pj both are false, and for some reason turn is I. Not necessarily that it should be I always, it can be anything, either I or j. So let's assume that it is I, and assume that both Pi, Pj till now we are not interested in entering any of the critical sections. So first line, Pi says I want to enter, and both of them are executing that instruction. So whatever we have seen in the previous slide, that set of instruction they are trying to execute line by line. So first instant process I's first line gets the chance, so it says flag I is true, so Pi's flag will become true. Again Pi gets chance to execute next, so it executes its second instruction, turn equal to j, so turn has become j. The next Pj got the chance to execute, not necessary that, as an example let's assume that in the third instant Pj got the chance to execute its instructions, so the first instruction in Pj was flag j equal to true, therefore Pj's flag also became true. The next instruction says turn equal to I, now it was j earlier, now it has become I. Now what? Let's assume that third line of Pj is given chance to execute, so what is it trying to say? Flag I and turn is equal to I. Flag I, what is flag I? Flag I already made true by process I, so flag I, it checks what is there in flag I, it is true. Then turn is equal to I. Now look at what is turn. Just now we had made it I, therefore turn is equal to I. Yes. Flag I is true. Yes. Turn equal to I is true. Yes. Both are true, therefore the AND operation is also true, therefore process J waits. On the other side what happens? We have same instruction being executed, the third instruction, because this is now waiting, let's assume that the third next chance is given to Pi. Pi gets a chance to execute next, so the third instruction of Pi comes for instruction, and again it is another while loop, so flag j and turn equal to j. Flag j, yes it is true. What is turn? Turn is still I. Turn was made j here, but after that at the second instant turn was made 0, but at j, but at fourth instant turn was made I, therefore currently the turn is still I, therefore turn equal to j is false. Flag j is true, no problem, so true and false is false, therefore this loop breaks, and therefore it doesn't wait there indefinitely, it just goes to the next line, and the next line is the critical section of Pi. On the other side this is waiting because flag I is true, turn is true, turn is I, therefore this is true, so it waits and waits. Then once the critical section of Pi ends, then finally Pi declares my critical section problem is solved, so let j takes care of its problem. So I will take back my flag and say flag I is false, and flag I becomes false. Now if you look at that, what J was doing, what Pj was doing, it was just looking at flag I and turn equal to I. Yes, turn is still I, but now flag I has become false. Therefore this indefinite while loop ends, because the moment the 8th step flag I is made false and flag I goes false, then this bracket goes false, and hence while loop breaks. Once the while loop breaks, it gets into its critical section, the Pj gets into its critical section, and then finally Pj declares false once its critical section is over. And on the other side, let Pj get into critical section, we don't mind the Pi is doing its other routine activities where it doesn't need any shared resources, therefore it don't have to enter into critical section. The other non-critical activities it keeps doing, and flag J is made false, and the moment flag J is made false, and then it also enters into critical non-critical region, remainder section. This is getting into this continued working in the remainder section, and this goes on. And next time when either Pi or Pj wants to use any shared resource, then again they will do this exercise, make flag high and then fix the turn and then while, and if only one of them, Pi or Pj, is wanting to enter, they just enter because other flag is false. If both of them want to enter, then this way either Pi gets chance first or Pj gets chance first, depending on who run these two instructions last. If turn J is run last, then J continues, I waits. If turn equal to I runs last, just as we have seen now, then J waits, I continues, and this keeps on doing alternately, sometime in critical section, sometime in non-critical section, again back in critical, non-critical, critical, non-critical, and that continues. So that's how we ensure that a critical section is taken care without disturbing each other. So what do you think, why it works? So first, mutual exclusion. Both processes set their flags to true and only one will proceed, depends on the turn. The turn variable ensures only one process gets in, the other is stuck in the while loop. Yes. Then talking about progress, only one process wants in, then turn doesn't matter, it just proceeds. But if both want in, then one will enter based on the turn and other waits, and once the other wait is complete, then the first one comes back and continues its progress. About the bounded waiting, the turn variable ensures that each process eventually gets a turn. So sometime I, then J, then I, then J, and so on. Because I is entering into critical section, it says J. If J is trying to enter critical section, it says I. And because the two processes only are deciding who to go into critical section, therefore progress is guaranteed. Outsiders are not allowed to decide who should go, I or J. Outsiders are not allowed. Two processes want to enter into a critical section, then only these two have right to decide who should go into critical section. Therefore there is progress guaranteed, and definitely the waiting is limited because the time each process takes to complete its critical section is bounded. Therefore once the critical section is done, definitely the second one gets a chance. So there is bounded waiting, and no process can indefinitely block the other. That's how we have to make sure that the critical section should work such that it completes in a bounded period, not that the critical section keeps on waiting forever. That's how the critical section should be properly designed. So that's an example. You can think of possibilities. If only P0 wants to enter, that is the first line we are looking here. P0 says it is true, that means flag 0 is true, and P1 doesn't want to enter, therefore flag 1 is false. So it doesn't make any chance whether turn is 1 or 0. So because this is false, so the wait for P0 is cancelled, so P0 gets into critical section. On the other side, if both are true, then if turn is 1, P1 goes into critical section. If turn is 0, P0 goes into critical section. So that's how the Peterson solution works. So that's it about the Peterson solution. It's for two processes only. It's a software based solution, and it ensures that all three conditions for the critical sections are met. So that's it about Peterson solution. Find this series of interest, please do like, comment, share, and don't forget to subscribe to this channel. Thank you.